Today we'll be meditating on the nature of buoyancy, and we'll come to learn everything there is to know about it, because we'll see how buoyancy arises inevitably from the nature of fluids and gravity. By the end of our meditation, buoyancy will become so familiar that you won't even need a word for it. You'll just see and feel how it arises naturally from simpler principles. Along the way, we'll meet some concepts from vector calculus, which we will see time and time again in our various adventures in math and physics. We'll approach these concepts in vector calculus from a visual and colloquial perspective, starting from a place of common sense, and then crystallizing those ideas into equations, so that the equations serve as precise, durable, and portable snapshots of our thought process, rather than as burdensome puzzles that we have to decrypt. So don't worry if you haven't studied vector calculus yet. Everything in this video will be accessible to a general audience. All you need is your imagination. Alright, let's get started. We'll begin our meditation at the molecular level, depicted here as a bunch of little circles bouncing around. As it turns out, the shape of the molecules isn't super important for our meditation. The main principle that we want to extract from the little cartoon that's on the screen right now is that when you have a bunch of molecules bouncing around off of a surface, so let's say this black line in the center of the board is the surface, well, sometimes the molecule will hit coming down, sometimes it'll hit coming up, and so there's forces up and down, but really those average out, and at the end of the day, when you add up all the forces of the impacts of those molecules, you end up on average with an outward force, in this case a force pushing on to the right. And so the principle that we want to extract from this molecular view is that if the molecules are bouncing around randomly, which they would be, for example, if the water is stationary, so from our perspective at the large scale there's no motion, but at the micro scale the molecules are all bouncing around with some thermal distribution of velocities. And when that's the case, then the various ups and downs balance out, and on average you get a perpendicular force on a surface. So that's the key principle. That's one of the two main principles that we need in this meditation. Hydrostatic pressure, pressure from fluid that is standing still, is always, it always acts perpendicular to the surface. For the second principle of our meditation, it'll help to define a coordinate system. So we'll use the coordinate system shown here. In this coordinate system, the xy plane is horizontal, and the z-axis is vertical. We set the origin point z equals 0 to be the surface of the water, and we'll let the z-axis point up. Notice that since the z-axis is pointing up, a certain depth will actually be a negative z value. So 10 feet deep is negative 10 feet for z. The reason we're doing this is because we could make it so that depth is positive, but then our z is pointing upside down. So I figure, well, we'll use z pointing up, and then we'll just remember, okay, if it's depth d, then that's actually coordinate z equals negative d. Okay, so now what's that second principle I mentioned earlier? Well, it's this. It's that for any still stationary body of water, whether it's a puddle or a pond or a lake, the thing that causes the hydrostatic pressure is the weight of the water. And specifically, it's the weight of the water above any given point. Because imagine you're underwater, you're looking up, the thing pushing down on you is how much water is above you. And a way we can mathematically formalize that is say, well, imagine a rectangle. It has some length, width, and height. The weight of that is just the weight density, in terms of weight per unit volume, times the volume of that rectangular prism. But we can shrink down the length and the width of that box, and we can just imagine when you divide the weight by the cross-sectional area to calculate the pressure, because pressure is force per area, the length and the width sort of cancel out, and really what determines the pressure at a given depth is the weight density of the water times the depth, because the depth is the height of that water column. And so we end up with this nice formula that the pressure is our weight density, by the way, the symbol gamma is used for weight density, times the depth of the water. So pressure equals gamma times d, where d is depth. Now we'll put that in our coordinate system. Remember, z is negative for deep stuff, so stuff underwater has negative z, so that formula becomes pressure equals negative weight density times z. If we plot this formula, shown here with the green arrows, we can see that the pressure increases as the depth increases. And in fact, it's a linear trend. You can see that it's a line with a certain slope. And it's interesting to think about what this means. So it means if you go twice as far down, there's twice as much pressure. Or 3 times as far down, there's 3 times as much pressure. Now I should say a couple of things. First, for this analysis, we're taking 1 atmosphere of pressure to be what's called our gauge pressure, which was basically the 0 point of our pressure. So the math of pressure works out in such a way that we can basically say the pressure of the atmosphere is going to be our 0 point, and all the math still works out because pressure is kind of a relative thing. The other assumption baked into this math is that water is incompressible, meaning that you can apply a pressure to it, but then it doesn't shrink in volume. So if you have a gallon jug of water and you squeeze on it, you'll induce a pressure in that water, but the water is not actually going to shrink. And that approximation is actually really good for water. It's surprisingly good. Water, you try to squish it sometime, you'll see you basically can't. And so anyway, this equation, pressure equals negative gamma times z, it's actually a very good equation, very precise, very accurate. So the other thing to say about this is think about gamma as being that slope factor on the equation. So the weight density of the water is the rate at which the pressure increases with an increase in depth. A higher weight density of the fluid is going to mean a faster rate of pressure increase as you go deeper. So imagine you're swimming in water. If you swim down 30 feet, you might get about an atmosphere of pressure. Well, if you're swimming in mercury, the liquid metal, then if you swim down 30-something feet, you're going to get many atmospheres of pressure because it's a denser substance. And in fact, there's not just a connection between weight density and the increase of pressure with depth. These numbers are actually precisely the same. This is actually the same number viewed from two different perspectives. And if you take nothing else away from this video, I think this is a really interesting and memorable observation. The weight density of a fluid and the rate at which it increases pressure with depth is actually the same exact number. I'll show you this calculation in case you don't believe me. So we'll start off with the weight density of water is about 62.24 pounds per cubic foot. Now if you look at the rate of pressure increase, typically if you go down 34 feet of water, you get about an extra atmosphere of pressure. So if you look at the fractions here on the bottom line, the first thing we do is we convert 1 atmosphere to 14.7 psi, and then we convert psi, in other words pounds per square inch, into pounds per square foot by multiplying by 12 times 12, so times 144. We get about 2,116 pounds per square foot. Now we divide that number, 2116 divided by 34 gives us about 62.24, and then a pound per foot squared divided by a foot is a pound per foot cubed. Now, depending on whether you're freshwater or saltwater, of course these numbers change a little bit, but that's beside the point. The point is that it's the same number looked at in 2 different ways. And it's not just a coincidence of this system of units. So here's the same calculation in metric, so you can verify it is actually just generally true that the weight density of water and the rate at which hydrostatic pressure increases with depth are actually exactly the same number viewed from 2 different points of view. So that's a little fun fact, and that'll play an essential role in where this video is about to go next. So I want to take a moment to summarize the 2 physical principles that we've come across so far in our meditation. The first one is that hydrostatic pressure, meaning the pressure of stationary water, pushes perpendicularly on a surface. The second principle is that the strength of the hydrostatic pressure is given by the weight density gamma times the depth d. In our coordinate system, we can write a pressure as a scalar field using the equation pressure equals negative gamma times z. Again, that assumes the fluid is incompressible. Okay, so that is the only basis in physical reality that we need in order to derive the equation for the buoyant force and everything we need to know about buoyancy. Now, in order to get there, we actually do need to import some mathematical ideas, which we'll get to in a moment, but the essence of the physical aspect of our meditation is completely shown here with our 2 physical principles. Now we need to go off on a quick geometrical tangent in order to prepare for our buoyancy calculation. Whether you count this as a physical principle or an exercise in abstraction ultimately comes down to your religious perspective. But in any case, it's important to know, and it is a fundamental feature of the world, and probably more than just our universe, that for every front there's a back, for every left there is a right, and for every top there is a bottom. If you're a shape, if you're some volume with some surface, you can't point your surface more in one direction than another. You're sort of, if you're a three-dimensional surface, you're exposed on all sides to space, at least, or to geometry, right? So it's kind of, you know what I mean, but it's kind of hard to say with words, and so we have to get into some equations to really elaborate on that thought. When we do so, we'll find that that language applies itself very well to a qualitative, or actually quantitative analysis of buoyancy. So let's get into it. Oh, by the way, one of the things I've had to think about when making this video is trying to make it as accessible as possible while also doing justice to the ideas and presenting them in their full glory, and not just giving you a watered down explanation or an over approximation, or I'm not going to talk down to you. And now the cost of that is that I might say things that for some people in the audience that haven't seen these ideas yet might be sort of like, what is that? I haven't seen that before. But let me just tell you first, the three concepts that you might want to know mathematically if you haven't seen them before for the rest of this video are the dot product, the divergence theorem, and the concept of a normal vector. And we'll kind of get into those as we go along. If you don't know what those are, if you haven't seen those before, one, I'd encourage you to look into them, and I'll put links in the description so you can read more about them, at least at a surface level. They're really good ideas to be familiar with, and they're super useful. But two, even if you're not necessarily an expert on those concepts, I think you can still follow along with the video, and there might be parts here and there where you might think, well, that step, I'm not exactly sure what happened. But even if that's the case, you'll still benefit greatly from seeing the overall derivation and exploration of ideas that's to follow. So don't worry if there is something you haven't seen before. Think of it as an opportunity to learn a new idea. And I think I can assure you that even if you're not really super mathematical, I think you can still benefit from the remainder of our meditation. And I think that the result will still be very satisfying for you as well, even if your background isn't super mathematical. Now, if your background is very mathematical, I think you're about to love what you're about to see. So here we go. Imagine a circle with a set of normal vectors as shown here. Now here I'm only showing a finite set of normal vectors. In reality, you can imagine that there are an infinite number of them, but for visual purposes, I'm just showing a finite set. Now let's think about adding up all these vectors. We want to be able to add up an infinite number of vectors, and the way to think about that is first imagine that we have some finite set of vectors, and each one has its own footprint. The normal vector we'll call n hat, because it's a unit vector, it has length 1, and its footprint we'll call ds. And that's short for differential element of the surface S. So you can think of ds, it's just one thing, it's not d times s, it's just a differential, meaning an infinitesimally small amount of s. Now the thing that we want to add when we're adding these vectors is actually each vector times the length of its footprint. So we're actually summing over the normal vector times ds. Multiplying the vector times the length of its footprint is what keeps the integral finite even as the number of vectors grows toward infinity, because imagine that if you double the number of vectors, the footprint gets cut by a factor of 2. So if you multiply the number of vectors by 10, well now the footprint is 1/10 of what it used to be. So this method of keeping the sum finite even as the number of vectors goes towards infinity allows us to consider this sum and take it to the continuous limit, which lets us do calculus on this situation. And maybe not many people know this, but the integral sign is actually an elongated s, because it means the same thing as sigma notation, but in the continuous limit of adding up an infinitely many things, each of which is infinitesimally small. Okay, now often with the integral, you will want to say, what are we integrating over? What space are we integrating over? What interval? And so here we'll put a subscript s, meaning we're integrating over the surface. And because it's a closed surface, in this case 2 dimensions, it's a closed loop, we'll add this additional symbol, this circle. And what that denotes is that we're integrating around the whole path, the whole closed path, and wherever we start, we're going to end up back where we started. When you see this circle symbol on a double integral, that means you're integrating over an entire closed surface, meaning the entire boundary of a volume of space. And we'll get to that later, but for now, just imagine we're summing up all of our normal vectors around this closed circle. Now, without actually doing any calculus, you might have anticipated by now that this vector sum is 0. Well, to be precise, it's the 0 vector, meaning it has no length. It's just like basically a point. Now, how do we know this? Well, the vectors balance themselves out. For every top, there's a bottom. For every left, there's a right. For every vector, there's its antipolar vector, which is pointing in the exact opposite direction. And so when you integrate over the normal vectors of a circle, of course the result is 0. Everything balances out. Now here's where things get trippy. Now what we have here is a mathematically precise way of saying that when you add up the normal vectors of a circle, the result is the 0 vector. But surprisingly, this statement is true in the much more general situation of any shape. So imagine instead of a circle we have just whatever shape, and we have the normal vectors to that shape. Well, if you add them up and you go all the way around, do a whole loop, integrate over the whole thing and add it up, it's always 0. It doesn't have to be a circle. There's no way you could deform a circle in order to make that sum non-zero. Now even if you poke a hole in this shape and give it like a donut shape or something, even then the sum is still 0, because the hole you poked also has a sum of 0 when you integrate those normal vectors, so 0 plus 0 is 0. So this is actually a general, true statement about the sum of normal vectors over any shape. And we can prove it using the divergence theorem. Okay, so let's go ahead and prove that statement. Because one, it's a really nice piece of vector calculus, which is beautiful and worth seeing. But also, and more importantly for the purpose of this video, seeing how this proof is done will set us up, will prepare us for the buoyant force calculation that we're about to do later on. Okay, so the first thing to look at is imagine our circle with our normal vectors. Now we're going to immerse it in a constant vector field, which we'll call v. V is just, in this case, two-dimensional, some a constant for the x component, some b constant for the y component. It's just a constant, uniform vector field. What the colors here represent is called the flux density of the vector field v through the circle. Flux density is a scalar quantity that's calculated by taking the dot product of v and our normal vector, so it takes on its maximum values and minimum values, meaning positive and negative, when the vector is parallel and antiparallel respectively to our normal vector. When the vector v is perpendicular to our normal vector, there is no flux. The flux density is this local scalar quantity that here we're color coding. Blue is high, red is negative, white is 0. And the total flux, the flux integral, the sum over all those fluxes, is 0. Now, we can prove that by making use of the divergence theorem. So the first thing to notice is that the divergence of a constant vector field, which is just the sum of the first constant dx plus the derivative of the second constant dy added together, that's 0, because constants don't change as you move in x or as you move in y. So since the divergence of the vector field is 0, it follows that the integral of that divergence within our shape, within the area of our shape, must be 0. So using the divergence theorem, which says that that area integral is equal to the flux surface integral, we know that that flux surface integral must be 0. And if that's the case, then we note that v is not a function of anywhere on the surface. It doesn't depend on the surface, and also the dot product is linear. So we can pull v out of the integral. Now we can imagine the entire integral of the normal vector over the surface as being a vector quantity that when dotted with v has to equal 0. Well, that has to be true for v which is coming in from any arbitrary direction, because the way we set this up doesn't make reference to a particular direction. And in order for that dot product always to be 0, it must follow that that second quantity, that integral of the normal vectors over the surface, must be 0. And so that's the proof that for any closed shape, when you do this integral over the surface, you get 0. And we know that this holds true for any shape because we never said it had to be a circle. We used the divergence theorem on an area that was enclosed by a perimeter, and that's generally applicable. You can use that on any shape. It doesn't have to be a circle. In fact, the shape doesn't even have to be two-dimensional. We can go ahead and just extend it, the same reasoning, extend it up into 3 dimensions. Now, by the way, I know some pure mathematicians might take issue with my use of ds for these integrals around the two-dimensional shape. Typically you want to use dl for that. But I must confess that when I was first learning about this kind of integral, dl and ds always confused me. I thought they were like two different things. Now, I know better now, but even still, I know how confusing this notation can be to someone who maybe is seeing it for the first time or hasn't seen it a whole lot. So I'm just going to be consistently using ds for the vector footprints. Sorry if that bothers you, but anyway, we're about to take things up into the third dimension anyway, so here we go. What we have here on the screen is the three-dimensional version of the reasoning that we just went through, and so I won't rehash it. It's the same essence of the proof. But here we've taken it up one dimension, and of course, since the divergence theorem still holds in 3 dimensions, the same reasoning is totally valid. Now, it turns out it was harder than I expected to animate a 3-dimensional surface with normal vectors immersed in a vector field, so I've kept the 2-dimensional picture here on the right, and if you imagine this little 3-dimensional guy on the bottom of the whiteboard, imagine that as being immersed in a 3-dimensional vector field, and then apply the same reasoning we just went through, and you'll see that, in general, when you take the integral of the normal vectors over a surface, whether it's a perimeter of a shape in 2D or the surface of a shape in 3D, when you take that integral, it's always going to be the zero vector. Alright, so now we've seen the math that we need, and we're ready to go back to physical reality and calculate the buoyant force on an arbitrary object. This will be really cool, because it'll apply to any shape at any orientation. It'll be a very general, universal result about the buoyant force acting on an object. Let's calculate the total net force on an object of the water pressure acting on its surface. Because force is pressure times area, the total force is the sum, or the integral, of all the little points along the surface of the pressure at that point times the normal vector at that point, because that's perpendicular, and we know that pressure pushes perpendicularly on the object. The negative sign in front of the equation is due to the fact that our normal vectors point outward by definition, but pressure pushes inward on the object, so that minus sign flips the arrow around. Now if you look at the two diagrams here, one of them, the 2x4, is being dipped in the water, the other one we have a rotating square. In both cases, the p times n hat with the minus sign are those arrows pointing in, opposite the direction of the normal vector, with the strength of the pressure at that point, and that big arrow in the middle, that sum, is the net force on the object as a result of the pressure all around the surface of the object. As a reminder, for both of these animations, the motion is only intended to show what the pressure field would look like for a variety of positions and orientations of the object. The pressure here is not actually due to the objects moving. So imagine that these objects are moving slowly enough that the water has plenty of time to move out of the way, and what we're seeing in every moment is that purely hydrostatic pressure distribution. That is, the pressure distribution that's caused just by the water relaxing under its own weight, and taking on higher pressure values the lower down it is, and the more water it has above it to have to support. Earlier, we derived that the hydrostatic pressure at a depth of negative z is given by gamma, which is the weight density of water, times negative z. So let's go ahead and plug that in for p to get an expression of our net force in terms of the weight density of the water and the coordinate z. What we'll notice right away is that the two minus signs can cancel out, and gamma, the weight density of water, is a constant, so we can go ahead and pull that out front of the integral, multiplying the entire integral by that gamma factor. What that gives us is a nice, neat equation. F equals gamma zns of F equals gamma times the integral of zns. That is to say, it's like the integral of the normal vector over the entire surface, which would be 0 if it was just that. But there's this factor of z, which is related to the depth, and that kind of skews things. It biases the landscape. It makes the integral, it makes the vectors longer the farther down you go. And so the solution to this integral will be similar to the result we saw before in some ways, and yet in some ways it will be different. Anyway, we're going to go ahead and solve this integral now, and derive that famous equation for buoyancy. Spoiler, the force is equal to the weight of the displaced water, but we're going to derive that right now, rigorously and mathematically, using vector calculus. This is going to be profound. One of the reasons I love vector calculus is that you can make these really general statements that are just true. It's a very, very versatile and useful area of math. So anyway, let's go. Alright, the first thing we'll want to do is notice that our equation for the force is a vector equation. So it has three components, an x component, a y component, and a z component. Because look, on the left side it's a force vector, and on the right side it's a bunch of constants, or a bunch of scalars rather, and a normal vector, and it's integrated, so that's going to be a vector as well. So let's go ahead and represent that vector as a list of its components. So here we have the x component, comma, y component, comma, z component. Now in these integrals, n sub x, n sub y, and n sub z are the x, y, and z components of our normal vector, respectively. And by the way, I know we've got a lot of integral signs here, but bear with me. Typically, if there's more than a couple integrals, my eyes start to glaze over and I get bored and I'm like, what is this? But I promise you, this will be a very satisfying derivation. So notice that all we've done here is just write the equation out in triplicate and project that normal vector onto x, y, and z respectively, so that we can calculate those force, the components of our force vector along the x direction, along the y direction, and along the z direction. The reason we did this is that now it'll be easier to solve these components one by one, and then repackage them back into the net force vector. Before going further analytically, let's take a moment to stop and think about this equation and think about what our intuition tells us. So first, look at the two components, f sub x and f sub y, so the first and second integral expressions there. The symmetry of the situation would seem to imply that the x component and the y component of the force should be equal. We might also expect, based on everyday experience, that the x and y components of the force should also be 0. Because if you think about buoyancy, generally it pushes you up, it doesn't push you to the side. And we're about to prove in a moment that that is always the case. Because you can think, well, what if you had a shape that was shaped in such a way that it faced more left than right, and so the hydrostatic pressure gave you an imbalance in the xy plane. And of course, now that we're experts on integrating the normal vectors around a surface, we know that it's not really possible for a shape to face more one way than the other. And so we suspect that we can have a very rigorous derivation of the fact that buoyancy cannot provide a force in the xy directions. And so we'll see in a moment exactly how we can show that, but just thinking it through intuitively, we can anticipate that. Now similarly, if we imagine this third component, the z component of the force, we see that there's this n sub z vertical component of the normal vector in there, and we know that integrating normal vectors is 0, but here we have a systematic bias of z, and so we might expect that, well, it should be non-zero. The force should push up in z because the pressure is higher for lower z, so there should be that imbalance that pushes up. And we can expect that we should be able to get a nice, clean, interesting formula out of that. Now, of course, we probably know that it's going to be the weight of the displaced water, but let's go ahead and prove that rigorously in the case of any possible shape. Okay, first let's calculate the force component in the x direction, which, as we've discussed just now, we think is going to be 0. Alright, let's write it out. So we've got gamma times the surface integral of z times the x component of the normal vector integrated over the whole surface. Now here we're going to do a fancy little math trick and say, well, z times the x component of the normal vector is the same thing as z, 0, 0, dot product the normal vector. Because think about it, that first term in the z00 vector, that gets multiplied by the x component of the normal vector, and then the y and z components of the normal vector get multiplied by 0 and 0, so what we're left with is z times n sub x. This is really an algebraic trick, and the reason we're doing it is because now it lets us leverage the divergence theorem, this time in the opposite direction as before, because we can notice, hey, this is a flux integral of the vector z00 dotted the normal vector integrated over the surface. Well, but by the divergence theorem shown here in blue, that's the same thing as the volume integral of the divergence of the vector field given by z00 integrated over the volume. And it turns out if you take the divergence of the vector field z00, what you end up with is partial z partial x plus partial 0 partial y plus partial 0 partial z. Anyway, what you end up with is just the partial derivative of z with respect to x. Well, z and x are perpendicular dimensions. Z doesn't vary as you take a step in x, so that partial derivative is 0, and of course the volume integral of 0 equals 0. So here we have a really solid mathematical proof that the x component of the force is 0. This is why if you lay in a pool in a certain position or direction, you're not at risk of being pushed to the side by buoyancy, because the x component is 0. Now, of course, we can apply the same reasoning to the y component, and this time we'll do 0, z, 0 for that vector. We'll pull the same trick, and we'll find that partial z, partial y is 0, and so precisely the same reasoning works, and we can show that the force in the y direction is 0. Of course, we can also prove that more elegantly just by rotating our coordinate system 90 degrees and recognizing the inherent symmetry of the problem in x and y. So what happens now when we apply this same reasoning to the z component of the force vector? Well, this time we'll use the vector 0, 0, z to pick out the product of z times n sub z. We'll use the same trick, noting that it's a flux surface integral, so you can write it as a volume integral of the divergence. But this time when we calculate the divergence of the vector 0, 0, z, we're left not with partial x, partial z, or partial y, partial z. Rather, we're left with partial z, partial z. And so, whereas previously partial x, partial z, or partial y, partial z is 0 because those dimensions are perpendicular to z, now we have partial z, which is 1, because the partial derivative of anything with respect to itself is always 1. If you take a step in z, you take the same step in z. It's like, it's just how it is. So what we have here is that the z component of the force is gamma, our weight density, times the volume integral of 1 dv. We can just write it as integral of dv, where these dv are these differential infinitesimally small volume elements, and the triple integral means we're adding them up in 3 dimensions of space. In other words, that integral, triple integral dv, is just a mathematically fancy way of saying the volume of the shape. And so we can just rewrite that as volume of the shape. But now think about what that means. The z component of the force equals our weight density, as in weight per unit volume, times the volume of the water that has been displaced. And so we can simplify it further, and we can say that the force in z is just the weight of the displaced water. And this is our beautiful formula for buoyancy. Let's go ahead and package it back into the force vector in 3 dimensions, just to highlight the point that there's no force in x, there's no force in y, and the force in z is the weight of the displaced water, and z points upward, so the buoyant force points up. If you came into this meditation already knowing the formula for the buoyancy of water, you might at first think, okay, well, I kind of already knew that. But consider this. Before, most likely, most people who have heard of the buoyant force formula, they just took it for granted as something to take on faith, as something that is like sort of a fundamental law of nature. But it's not a fundamental law of nature. It's an emergent law, and it arises from the deeper principles that we've talked about today. Well, so who cares about that? Why does that matter? Here's why it matters. The world around you is like a kaleidoscope, in that it is the multifaceted expression of a relatively small set of principles. And so, the fewer mysteries you need to explain the world around you, the more in touch you are with the fundamental nature of things. Now there's many ways to think about that, but one objection that'll often come to mind is, isn't there a risk of overly reducing the beautiful phenomena of nature to just a small set of things? Doesn't solving mysteries take the zest out of life? Isn't it better to imagine a worldview that's more colored and textured and dynamic and vibrant? And doesn't it take something away to reduce it to a small set of principles? And that is a problem that I personally struggle with and that I take very seriously. But all I would say is this. It's not up to us how nature is. And if there are these hidden simplicities in the world, then I think it's important not to be captivated by the wrong set of miracles. I think it's important to be captivated by the true miracles, the true mysteries. And so I think that there is something very healthy and very mentally cleansing about seeing the simple patterns in nature wherever one can. And I trust and I have faith that nature is plenty beautiful and extraordinary and mind-blowing, that no amount of reductionism will ever make it something that we look at and say, Oh yeah, that nature stuff, I got that. Obviously, this is a very simple place to be. No. There's always an inexhaustible well of complexity, beauty, and extravagance wherever you look. You just have to know what to look for. Okay, well, I think that's about all I had to say about buoyancy. I hope you found this video helpful. And please let me know if there's anything, if you have any questions, any comments, I'd love to hear them. And thank you for watching.